Today we are going to discuss disaster recovery for containerized applications on OpenShift. Hey, what's up everybody? Welcome back to my channel. My name is Aleš Nosek and I'm the software practitioner located in San Diego, California, helping you navigate the world of Kubernetes. Recently I worked on a customer project where we implemented disaster recovery. In this two-part video series, I'm going to walk you through the design and implementation of this project. For this video, I'm going to use many of the slides that I created for the Red Hat Summit presentation regarding the same project. I divided today's presentation into two parts. In the first part, we are going to review the architecture which we came up with to address the disaster recovery needs. In the second part, we are going to start looking into the details of our disaster recovery. So let's get started with the architecture overview. In this diagram, you can see that we leverage two AWS regions. The AWS West region is our primary region. And then we also use a AWS East region as our secondary region. In addition to AWS regions, we also have some of our application dependencies still located in private data centers, like for example, Oracle databases and other services. Note that because we are using only two AWS regions, our applications are protected only against a disaster in a single AWS region at a time. In the case that there will be disaster in both AWS regions, then our applications would not be available. We use several OpenShift clusters to host our application workloads. In the diagram, they are depicted using the blue color. You can see that we have a pair of pre-production OpenShift clusters. And also we have a pair of production OpenShift clusters. Pre-production clusters host several environments. Those are dev, test, and stage. On the other hand, production workloads are running in their dedicated production clusters. We decided to have a separate pair of production clusters so that whatever is going on in the lower environments will not affect our production workloads. We needed a pair of pre-production clusters so that we are able to test our disaster recovery procedures outside of production. Applications are deployed into both primary and secondary clusters at the same time. However, the application traffic is routed only to a single cluster. Under normal circumstances, the application traffic is routed to the primary cluster. Only if there is a disaster in the primary cluster, we can then fail over to the secondary one, and in that case, the traffic would be served by the applications deployed in the secondary cluster. Note that in our terminology, the clusters in the AWS West region are always the primary clusters, and the clusters in the AWS East region are always called the secondary clusters. We do not change the designation of primary and secondary, for example, because of a failover. In other words, in the case that we are failing over into the secondary region, then we say that we are operating out of the secondary region. We do not rename the secondary cluster or secondary region now into the primary. Some of our stateful applications store their data into AMQ Streams. AMQ Streams is a Kafka cluster deployed on top of OpenShift. In order to be able to fail over from primary to the secondary region, we also had to make sure that the data stored in the primary Kafka is replicated to the secondary Kafka as well. And for that, we used the Kafka Mirror Maker 2. This is an asynchronous replication, so we cannot really guarantee that there will be no data loss during the failover. However, based on our requirements, some data loss during failover was acceptable, and so we were able to use the asynchronous Kafka Mirror Maker 2 replication. I'm going to talk about the data replication in more detail in the second part of this video series as well. The last OpenShift cluster I wanted to talk about is the management cluster depicted here in red color. This is a dedicated cluster which hosts our GitOps tools, Red Hat ACM and Argo CD. We use these tools to configure the other OpenShift clusters as well as deploy applications, and also these tools help us and automate some part of our failover procedures from the primary to the secondary region. There is only a single instance of the management cluster deployed in the whole architecture, and the reason for that is cost. we wanted to keep the cost of the whole solution as low as possible. The management cluster is by default deployed in the secondary region. The idea is that in the case that there is a disaster in the primary region, then we could use the tools on the management cluster in the secondary region to fail over the applications from the primary to secondary. On the other hand, if there will be a disaster in the secondary region, then our applications in the primary region are happily running and serving traffic, so there will be no immediate need to use the tooling on the management cluster. However, if the disaster in the secondary region should take longer time, then we have the ability to redeploy the management cluster in the primary region as well. And for that, we would use the Ansible automation to deploy the tooling, and then we would restore the state of Red Hat ACM from the backups, which are being created in the S3 bucket in the primary region. We are using GitOps for managing our OpenShift clusters as well as for deploying applications. And if you use GitOps, you need to solve the secrets management as well, because you don't want to store secrets in Git. In our case, we chose the AWS Secrets Manager to store our GitOps secrets. This AWS Secrets Manager service has the great ability to also replicate the secrets from the primary to the secondary region. In order to get the secrets data created as secrets on OpenShift clusters, we install external secrets operator on each of our clusters. And this external secrets operator pulls the secret data from the AWS Secrets Manager from the same region. So there is no cross-regional communication in order for the external secrets operator to pull the secret data from the AWS Secrets Manager. It's always the same region. One last note I want to make before we move on with the presentation is the note about latency. As you can see in our architecture, we are leveraging two AWS regions. One of them is on the East Coast and the other one is on the West Coast. And we also leverage private data centers as well. Before we started building this architecture, we did a proof of concept to prove that our applications will be able to tolerate the latency, the substantial latency, which is here between the two AWS regions and our private data centers. Now, before you go and start building and put the effort into this architecture, you should make sure that your applications are happy with this kind of latency as well. We use some good practices while building the architecture that I would like to share with you. When working on your disaster recovery strategy for your applications, you will also need to review all dependencies of your applications. Those are dependencies like Oracle databases and other services that your application requires in order to be able to function. In our case, we discussed the individual application dependencies with the teams that owned these dependencies, and we were interested to understand what is the disaster recovery strategy for a given dependency, and in the case of a failover, how would our application be able to reconnect after the dependency failed over. Another practice that worked well for us was trying to keep the architecture as simple as possible. You have, for example, seen in the previous diagram that we used a single instance of Argo CD. At the scale we are at, where we are only managing about 4 to 5 clusters, one Argo CD instance was performing enough to manage them all. Also, in our case, it is a single team that is managing the configuration of the clusters as well as deploying the applications. So there was no real reason to introduce another instance of Argo CD. In the future, if our environment keeps growing and we will be introducing additional clusters into the picture, we could switch to the model of using one Argo CD per cluster. We didn't want to really introduce one Argo CD per cluster right off the bat because of the complexity of managing multiple Argo CDs. The more complex your architecture is, the more complex and less reliable will your disaster recovery be. So start simple, and you can always iteratively introduce more complexity if needed. And the last practice I wanted to mention is keeping the architecture decision records. When working on a more complex project, it is always good to keep notes about what decisions have been made throughout the project, and also what were the pros and cons of different alternatives which were compared when making the decision. This helps to keep the team members aligned while executing the project and serves as a great documentation after the project is finished. Over time, the reasons which led to certain decisions may change. If you are keeping your architecture decision records, you will be easily able to go back and reevaluate your existing decisions based on the new information. Let's now focus on the details of our disaster recovery strategy, and let's start by reviewing the objectives. Number one objective of our disaster recovery strategy was to protect the applications from downtime. The applications are the ones that generate revenue, and our strategy is here to really protect the revenue for the company. So that's why we are focusing on applications in the first place. It can happen that, for example, some of the components of OpenShift, like control plane components or operators, will not be working well or have an issue. However, as long as this does not affect the application, then it is not really a disaster for us. When creating your disaster recovery strategy, you will need to determine the recovery point objective and the recovery time objective for each of your applications. The recovery point objective defines the maximum amount of data that you are willing to lose during a disaster. If you are fine with losing up to several hours of data due to a disaster, then you could use periodic backups to meet this objective. If, for example, you are fine with losing a whole day of data, then nightly backups will do. If you cannot tolerate to lose more than minutes of data due to a disaster, then you are looking at using continuous replication of data. And in this case, an asynchronous replication would be able to meet your objective. If you cannot afford to lose any data, even during a disaster, then you are looking at using synchronous replication. The recovery time objective is the maximum amount of time that the application can be down due to a disaster. In other words, it is also the maximum amount of time that it can take to restore the application after a disaster. This time typically includes the restoring of application data, the scaling of the application in the secondary region, and then also rerouting the application traffic to the secondary region. Based on the agreed upon RPOs and RTOs, you can group your applications into different tiers. The tier 1 applications would be the most critical applications, which should be restored very quickly and also are not tolerant to lose much data. On the other hand, tier 2 and the other tiers would be less critical applications where the recovery of them can take longer time. The next disaster recovery objective we had was that we wanted to protect our applications against data corruption or accidental data deletion. These kind of disasters can happen, for example, due to a software bug where the new version of the application starts corrupting the data, or it can also happen due to a human error. Note that continuous data replication will not help you against these kind of disasters, because as the data is corrupted in the primary location, it will be copied exactly like that into the secondary location as well. So you will get corrupted data on both sides. What helps against data corruption is periodic data backups. In our case, for example, we were backing up our data from Kafka clusters using Velero. The last DR objective we had was that we wanted to protect our applications against infrastructure failures. And this can be achieved by using redundant infrastructure. In our case, we are using multiple availability zones within a region, and also we are using multiple regions. As soon as you start using redundant infrastructure, you will also need to replicate the data which sits on top of this infrastructure. Otherwise, it would make no sense. In addition to that, you will also need to figure out the application traffic routing. In the rest of this video, I will discuss the basic approaches for using redundant infrastructure, and the details about data replication and traffic routing will be left for the follow-up video. I will include the link to the follow-up video down below. So let's now focus on approaches of using redundant infrastructure to protect our applications against infrastructure failures. The AWS well-architected framework proposes several approaches. They can be divided into two groups based on the traffic routing. In the active-active approach, the application traffic is routed to both regions at the same time, so both regions are actively serving the application traffic. On the other hand, the active-passive approaches, there the application traffic is only routed to a single region and served from there, while the other region is just a passive region which is receiving no traffic. There are 4 different active-passive approaches: the backup and restore, the pilot light, the warm standby, and the hot standby. These approaches differ in how fast they allow the application to recover. The faster the recovery, the more expensive the approach is. In the following slides, I will discuss these approaches in more detail. Let's start with the active-active approach. In the diagram on the left side, I'm showing the normal operation, where you can see that the traffic is routed to both regions at the same time, and so both regions actively serve the application traffic. In the case of a disaster in the region, we just reroute the traffic to the remaining regions. The compute resources in the regions should be configured to autoscale, so that in a case of a regional failure, the other remaining regions are able to meet the additional traffic demands. From all the approaches presented, the active-active approach provides the most reliable recovery because it is part of the normal operation that all regions are exercised using the application traffic. The problem with the active-active approach is that the application needs to be pretty much designed to be able to run as active-active in multiple regions. If you are creating a disaster recovery strategy for existing applications, the chances are that those applications won't be able to run as active-active, and you will need to choose one of the active-passive approaches. The first active-passive approach I will discuss is the backup and restore approach. As with all active-passive approaches, the application traffic is routed to a single region. In the case of a backup and restore, the application is deployed into a single region only. And then application backups are created periodically in the standby region. In the case of a disaster in the primary region, we will need to restore our application data from the backup in the secondary region. And after that, we can deploy our application and start it. And as a last step of the recovery, we can promote the secondary region into an active region by rerouting the traffic into this secondary region. The backup and restore approach is cost-effective. It doesn't require any compute in the secondary region during normal operation. However, recovery using this approach is rather slow, as part of the recovery procedures is restoring data from backups, as well as scaling your application up from 0. The recovery is also less reliable because the application was not running in the secondary region before, and now that we are bringing it up, we hope that it will just work. In our architecture, we use the backup and restore strategy for recovering Red Hat ACM. Let's now look at the next strategy, which is called Pilot Light. This strategy is an improvement over the backup and restore strategy. The application is again deployed into a single region only. There is no application running in the secondary region. However, instead of just pushing backups from the primary to the secondary region, we actually have application services running in the secondary region as well. In our case, this was a Kafka cluster, which was deployed into the primary as well as the secondary region. And there is a data replication, continuously copying data from the primary to the secondary. Because the data services are already running in the secondary region, the disaster recovery is faster. To recover, we just needed to stop the data replication from the primary region. And after that, we can deploy and scale up our application and reroute the traffic into the secondary region. The next approach I want to discuss is warm standby. This approach is a further improvement in comparison to previous approaches. With warm standby, the application is deployed into both regions. However, the deployment in secondary region is scaled down to a bare minimum to save compute resources. This brings the benefit that we can monitor the application in the secondary region for readiness, for example, using synthetic monitoring tests. The failover into the secondary region is less risky because we know based on our checks that at least some basic functionality works in the secondary region. Before we can reroute the traffic from the primary to the secondary region, we will need to scale up the application in the secondary region. The last approach, the hot standby, differs from the warm standby only in that the application is deployed into both regions at full capacity. This approach wastes compute resources, as the compute resources in the secondary region are normally idle. However, it was a good initial approach for us as it is easy to deploy. we could use pretty much the same Kubernetes manifests and just point the Argo CD to the other region. Let's review what we covered in this video. We reviewed an architecture which spanned 2 AWS regions and which was able to recover from a failure of a single region. The architecture included 2 pairs of workload clusters, as well as 1 management cluster. This management cluster was used to host the tools like Red Hat ACM and Argo CD. I walked you through the main disaster recovery objectives we had on this project. The number 1 objective for us was to protect the applications from downtime. And for that, we had to define the recovery point objective and the recovery time objective for each of our individual applications. We used data backups to protect against data corruption and deletion. And we used redundant infrastructure to protect against infrastructure failures. There are several approaches for multi-regional disaster recovery. We discussed the active-active approach, and we also reviewed several active-passive approaches like backup and restore, pilot light, warm standby, and hot standby. In the second video of this series, I'm going to discuss the application traffic routing as well as data replication between regions in more detail. I will include the link down below. I hope you enjoyed today's video. Please feel free to leave your questions or comments down below. If you found this video helpful, please consider subscribing so that you are notified whenever I release a new video. Until next time.